So, here's where we ended yesterday. Ooh, I got to get to insert real quick, actually.
Mr. Wiz. When do you get your
Monday at 4 p.m., I think.
Sorry. Everyone's here. Good. Makes it easy. So, yesterday we talked about a pebble. Alright, that was dropped into a calm pond. For some reason that seems like a hard thing to say. Calm pond. It's like rural juror. Rural. Okay. Rural. So let's continue with this pebble idea, right? So the pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Oh, sorry, there you go. The radius r of the outer ripple is increasing at a rate of 1 foot per second, I guess. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Okay, so let's change that. Let's look at that using the information above. All right, let's change it up a little bit just to see what happens. At what rate is the circumference? Just kind of using the information above. At what rate is the circumference of the disturbed water changing? Okay, so we're going to use that same information now, but we're only going to look at what rate, missed the word rate. At what rate is the circumference of the disturbed water changing?
I copied that verbatim and I did the same exact thing.
Yeah, sometimes when I write something and then I break from it and I come back to it, I miss the word.
Yeah.
Verbatim?
Verbatim.
You said verbatim. I was like, what? Verbatim.
Okay, so again, let's follow our steps, all right, to kind of set this up. So let's see here. We're told step 1. I'll kind of scoot this thing. Scoot it. It's going to fit. Barely. Not really. Okay, so number 1, identify all given quantities and all quantities to be determined. So again, from our information that we're given here, pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Okay, so there's information, but nothing like necessarily that we need to use right there. The radius r of the outer ripple is increasing at a rate of 1 foot per second. So is this r equals 1? How do you know it's not r equals 1? It's a rate of r. How do we describe the rate of r in a related rate problem? dr dt. So dr dt is still going to be 1 foot per second. Okay, so that's one of our values we're given. Okay, when the radius is 4 feet, so now that's not a rate anymore. That is a radius. So we want to find at the instant when the radius is 4 feet. Okay, and then we have to go down here. Now we're going to use this. We're going to find the circumference. So that means we want to find c. So I'll do like capital C, and we want to know what does that equal. Oh, at what rate is the circumference change? So it's dc dt. My apologies. dc dt is what we want to find because we're trying to find the rate of change of the circumference of the disturbed water. So that's what we want to find. dc dt is our question mark there. So what formula can we use to relate circumference and radius? Okay, so circumference is what? Yeah, pi times diameter. Now, right, exactly. We wouldn't want to use this version of the formula because do we know anything about the diameter? Well, kinda. We know the diameter would be twice the radius 8, but we wouldn't know what dr dt is. I don't want to say we should just double that because I'm not sure that would be right. So we want to change this in terms of radius, so it'll be 2 pi r. That's what we really want to use there. Okay? Yeah, so we want to use the circumference equals 2 pi r. Okay. Now, Christian, do I plug in my numbers right now? No! What do we do? First step.
Take the derivative.
Take the derivative. So let me number these here. So there was 1, we identified our numbers, our values. 2, we wrote an equation that related the variables. And then 3, we're going to take the derivative of both sides here with respect to time. Okay, so Christian, derivative of c with respect to time is what? dc dt.
No, I see.
And the derivative of 2 pi r with respect to time, Christian?
2 pi dr dt.
2 pi dr dt. Okay?
Trying to get there real quick.
Exactly right. Now I can plug stuff in. So I'm going to go to Anna. So now that we have the derivative, Anna, okay, step 4 says to plug in the given values and solve for the required or the asked for rate of change or whatever. So step 4 here, I guess I'll do it like up here. All right, so it's like 1, 2, 3, and then 4. Okay, so can I plug anything in for dc dt, Anna? Okay, so we're solving for dc dt, so we're going to leave that. You said 1 goes in for dr dt? That's right. Notice here, Anna, where do I plug this 4? Whoops. We don't use it. We don't use it at all. In this case, we don't use the r. The radius for the circumference, for the rate of change of the circumference, the radius, what its measure is, has no bearing on the rate of change of the circumference. Okay? So whatever length the radius is does not matter for the rate of change of the circumference. Rate of change of the circumference is only dependent on dr dt. This is kind of like what I was talking about earlier with Emma when she was talking about this. The rate of change of the circumference is only based off of the rate of change of the radius, and that's it. Times 2 pi, but, you know, that's the only thing that affects it. The radius itself does not affect. What the actual radius length is does not affect it. Just how the radius is changing affects how the circumference is changing. Okay? So then it's 2 pi, right? And then what would our units be here? Anna, what do you think? What would the units be here? What's that? So feet per second, exactly right. How'd you get that? What's that? Just the units that we're using? Yeah, so what were the units for the 1 here? Feet per second. And then times 2 pi, those are just constants, so that'll just keep it in all feet per second.
Did you say 6.28?
If you wanted to. Well, actually 3 decimal places, so 6.28. What's that? It's 2 pi. 6.283 is what it would be. Okay, feet per second. But I like leaving it as the precise answer, because I don't have to worry about rounding incorrectly or anything like that. Okay, that was it.
Make it harder, Mr. Whittaker.
Right, now let's make it harder. Oh, you got it, Christian. Oh, Christian, thank you. Yeah. All right. I gotta go use
One thing I'm learning about math is it always seems easy at first, and then it always has a way of making itself extremely.
Well, it's what we call that, like, I guess, like scaffolding, I guess I want to say, or something. I don't know. But it's basically like you want to start with an easy example, so you get like the basic concept down, and then you add layers of complexity to it. You give you the hardest one at first, you're like, this is impossible.
And
so
then every time I'm like, oh, this can't get any more difficult than this. Like, this is such an easy concept. It's not going to get more difficult. And then, like, they throw something like break into it. You're like,
okay. Air is being pumped into a balloon. So we're kind of going back to our balloon problem at a rate of 4.5 cubic inches per minute. Okay. Find the rate of change of the radius of the balloon. Okay, so air is being pumped into a balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius of the balloon when ...
Oh, this is going to be a...
We're going to do 2 different situations. Okay, so air is being pumped into a balloon at a rate of 4.5 cubic inches per minute to find the rate of change of the radius of the balloon when A ... dot dot dot, the radius is 2 inches. Okay. So again, let's go to our steps. All right, let's go to our steps. The first step, we want to identify all given quantities and all quantities to be determined. So let's see here. So go to someone else. I was going to call you awesome. But, all right, Caleb. So what kind of information, or what's in a piece of information we're given here that we can use?
The rate of change of the volume.
Yeah, the rate of change of the volume. What kind of clued you in that that was rate of change of the volume?
Cubic inches.
So right, we're saying cubic inches per minute. Remember, a volume is measured in cubic units of measure, so cubic inches per minute, that would be a volume. So that we would call that then dV dt, the rate of change of the volume with respect to time. That's going to be 4.5 inches cubed per minute. All right. Since we're talking about the volume of the balloon, that's going to be a positive 4.5, right? We could say, like, if, like, for example, if the balloon were deflating at that rate, and we're going to find the rate of change of the radius, then we would say a negative 4.5. So always keep in mind the idea of, like, are we inflating the balloon, or are we deflating the balloon, right? Is the circle getting bigger, or is the circle getting smaller? Keep those in mind. You sometimes have to throw negatives in to change the kind of like the direction of the flow, okay, kind of thing. So, but anyway, that's right. All right, are there any other values we're given here, Caleb? R is 2. Okay, very good. And so, is there anything else? What about the thing? We haven't figured out which thing we're supposed to find yet.
The rate of change of the radius.
Which we would denote that as what?
dr.
dr dt. Okay. That's right. It's the pirate. RDR. So this is all step 1 right there. Okay. We've identified the quantities and the quantities to be determined. All right. What units, by the way, Caleb, would we expect that dr dt to be?
Inches.
Yeah, very good. Radius will always be measured as a linear measure, so it's not going to be the cubic, it'll just be the inches. And then per time, well, the only time measurement that we have here is minutes, so it will be inches per minute. So that's helpful. If you guys aren't able to come up with that here, that's okay, but you need to be able to come up with it by the end of the problem, right? But I just figured I'd ask Caleb to see if he could do it, and he did, so nice. All right, so step 2, we got to write an equation now. I'm going to go to Tyler. T-Rock, Trock. All right, so what is the formula, right? What's the equation that we can use to relate all these variables? Well, no derivatives yet. We want to come up with the original equation. So what's like the thing that relates all this? What's the big formula, big concept we're talking about here? The balloon's being pumped up. We're trying to find, and we have the rate of change of the volume. So what kind of formula are we going to use here? This is maybe a little bit tricky. You have to use a little bit of interpretation. The volume of the balloon is changing, right? So we want to come up with a formula for the what of the balloon. We want to use a volume. In order to find the rate of change of the volume, we need a volume formula to then take the derivative of. So we want to find the volume of a balloon. And again, what kind of shape would that roughly be? Well, yeah, for our balloon, we'll say it's a sphere. I mean, some balloons are more likely, would be maybe resemble like a cylinder, like those long ones they use for like the animals and stuff like that. But for our balloon, it's going to be one of those sphere ones. So we'll say volume equals 4/3 pi r cubed. Okay, is the volume. Yep. Or again, like I said, I think you would be given that formula. I think you'd be given that formula. Not a formula sheet, but it'll be given to you in the problem. It'll be like, remember, volume of a sphere is blah, 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 or volume of a cylinder is blah, 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 kind of thing. Okay, great. So we got the volume now. What are we supposed to do next here then? We found the equation, and step 3 says differentiate both sides with respect to t. So I'm going to have you do that too, Tyler, since you just have that formula there. So what's the derivative of v with respect to t? dv dt. Okay. And then what's the derivative of 4/3 pi r cubed with respect to t, Tyler? 4 pi, what's the derivative of r cubed with respect to time? The 3 goes out front, you were right, 3 times 4/3 gives you 4. There you go, then dr dt. Yeah, be careful, a lot of people miss, or not a lot of people, but enough people miss that on the quiz, right? Be careful, we're so used to seeing a square here, when the square goes out front, then it's a 1, so we don't write the power, but remember, you're subtracting the power, every time you take the derivative, subtract the power by 1, so it's a 2 that's left there. Okay. Alright, great, thank you, Tyler. So now, Nate, I've got my rate of change, my volume here, Nate, so now what?
Now it's when we substitute in R and ddt.
Okay, great, so let's see, what goes in for R?
2.
2.
Well, 2 squared.
Right, well, it'll be 2, yeah, squared, and then dr dt, because that's what we're solving for. And then what goes in for dv dt?
4.5.
4.5. Okay, so there's our work. And so, Nate, we have to, are we done? What do we still have to do?
We have to solve for dr dt.
Right, and so if you guys want to, if this were a free response question, you could just do this. dr dt equals 4.5 over 4 pi times 2 squared, and then say, there it is, except we should put units, right? Nate, what would the units be here? Not inches cubed, that's a volume, this is a radius, so it would just be inches per minute. And so there's your answer. Alright, you can stop right there and say, I am done. Okay, if you want to, we can also do the decimal places too. So you can say 4.5 divided by. Don't forget to put parentheses around your denominator if you're going to do this all at once.
Oh, what you?
Okay, so about 0. Oof. Yeah, if we're going to round, we would put 0.090. If we're going to truncate, you can put 0.089. So I'm going to round because that's what I normally do. So 0 truncate, like Truncate. Truncate. It's like trunk. Chunky cake. Yes. It would round the 5 up to 0 here and then 9 here, so he's 0.090. You got that? Okay. Yeah. So again, if rounding's not your like forte, if you're like get messed up, just cut it off. Just cut off and say boom 0.089, and that's fine. Just be consistent though. Don't round one place and then truncate another. Always do one or the other. Okay. Let's try another one then. Part B. So now we're changing the situation. The radius is no longer 2. So ignore that previous piece of information. That's not true anymore. This piece is true, but the radius is no longer 2. So ignore that. We're going to now say, okay, now find the rate of change of the radius of the balloon when ... the circumference of the balloon is 20 pi inches. Okay, so now we're changing up the problem a little bit. We still want to find dv dt, right? Still want to find that, or sorry, dr dt. We want to find the rate of change of the radius of the balloon, but we want to find it when the circumference of the balloon is 20 pi inches. All right. So far, so good. All right. So let's dive into this here. So step 1, same steps as before. We want to identify what we're given and what we're trying to find. All right. So I'm not going to just assume that we, already did that before, even though we did. So Brandon, what are some values that we're given here? Okay. dv dt is what? 4.5 inches cubed per minute. Okay, great. What else are we given here, Brandon? Circumference. So we'll say C, capital C, is 20 pi inches. Okay. Are we given any other piece of information here?
No, we need to solve for dr dt.
We're going to solve for dr dt. Okay? And again, that'll be something in inches per minute in this case. Okay, cool. All right, step 2. Thank you, Brandon. Step 2, we want to come up with an equation that relates these things. So, Christian, any idea here? What should we use?
Relate.
Right.
Is volume like one?
Yeah, we're going to use volume here. Even though circumference is given to us, we still want to use volume. Why? Because the volume's rate is given to us, and it relates to the R still, which is, again, we want to find that rate of R. So we still want to use these to help guide us. But you might be saying to yourself, but Mr. Widmeyer, when I go write that volume down, 4/3 pi R cubed, the circumference is nowhere to be seen in this problem. There's no C in there. But why do we what can we use this C to find? The radius. The radius. So this is like a secondary kind of piece of information right here. The primary piece of information here, the things that we want to shoot for, we have a rate of change of the volume and a rate of change of the radius. So our equation has to have volume and radius in it because of the rates there that we have. Circumference is like a secondary piece of information we're going to use to come up with the radius there. So Christian, what is the derivative of this with respect to t? So derivative of v with respect to t is what?
dv.
dv dt.
Yeah. And 4 pi r squared.
And then 4 pi r squared
dr dt.
dr dt. R dt.
Cancel just 10.
Okay. So again, there's our rate. We took the derivative of both sides. Great. All right. So Donovan, can I plug anything in for dv dt?
Oh, yeah, sure.
4.5. You got it. All right. Can I plug anything for r here? Are we given an r? No. All right. We'll skip that. What about dr dt? Can I plug anything in for dr dt? No, in fact, that's the thing we're solving for, so I need to have the dr dt in here. So I need to come up with something for the radius, because I need to have dr dt. I'm solving for that. I need to figure out what r is. Donovan, how can we solve for r here? What can we do to solve for r? What other piece of information haven't we used yet over here? How is circumference related to radius? C is equal to what? It's kind of like secondary work over here. Do you know what the circumference formula is? No, 2 pi r. Okay? So, if C is 20 pi, what can I do here to solve for r, Donovan? Divide both sides by 2 pi. You got it. So the radius is 10. So that's we can plug in there. What's that? It's a big number. Right. Okay, so 10 squared is 100, times 4 is 400, so it's 400 pi. Again, you don't have to. You can just like divide this quantity over, put 4.5 over, this quantity right here, and be done. You don't have to simplify it out. For this, whatever reason here, I've decided I'm going to multiply it out, just to change it up and make it confusing, I guess. So dr dt is equal to 4.5 over 400 pi.
Nice.
And again, that's in inches per minute, which if we do that as a decimal, 0.004, I guess I'll say if you round.
Wow. It's 4.5 over 400 pi, correct, Mr. Wood?
Over 400 pi?
Yeah.
Yeah.
I'm not the reserves after the decimal place. You just say it's 0.
Hopefully the last one will round up. It shouldn't though. Like in a real problem, it should not do that because you're right. Otherwise.
So, Mr. Wood,
Yep.
I think I'm being stupid, but I'm not getting a second 0, and I typed it in correctly, and I don't know why.
So let's take a look here, guys, and see.
No parentheses.
Right, so what is his calculator doing?
I agree.
Yeah, 4.5 is only, no, but like, Austin, I appreciate this. Miro, I'm not trying to shame you because other people make the
I
same
should be
mistake.
shamed.
No, this is not, it's not shameful. No,
That's
it's
95%.
important. Learning experience. Shh, it's very important. Shh, listen here, guys, look. Here's the thing, right? We need to know how to use this piece of technology. This piece of technology is, like, old. They have not changed the operating system for these calculators since I've been in middle school, right? So that was, like,
Yeah, they still call us like 200.
over, well, it was about 15 years, 16 years ago. Anyway, regardless, they have not changed these operating systems, right? You guys are so used to using your smartphones with like either Android or the Apple operating system on it. These things are not very intuitive, so we have to be super careful about how we type things in here because it's different than how you might type things elsewhere. So just please be careful. Yeah, the way this calculator is reading this is 4.5 divided by 400 times pi. I wanted to make sure it was dividing by the quantity 400 pi, so you put parentheses around it. In general, make sure you just put parentheses around your numerator and denominators when you're working with fractions in your calculator. Okay? Thank you, Austin, for that demonstration. Dunce cap, right.
Never thought that would happen.
We should get
Right.
a dunk cut in this class.
Well,
You're wearing it like all the time.
Austin, it's a good thing. It's humbling. It lets people know that you make mistakes. Okay, that happens. You're human. That's okay. Moving on. Let's do one more here. I'm gonna have you guys try this one on your own. I should have enough space. You should have enough space if you have this much space here too. Okay. The radius R of a circle.
It's like a whole new problem.
Whole new problem now. That's why I put the little squiggly line.
Should have known.
I know, right? Okay. The radius R of a circle is increasing at a rate of 2 centimeters per minute. At the instant the radius of the circle is 6 centimeters. I want you to find A, the rate of change of the area, of the circle, and B, the rate of change of the circumference. Okay. Of the circle. Okay. All right, so I'm pushing you out of the nest, guys. Your turn. Time to fly.
I just fell on purpose.
Uh-oh.
That's an example not for Oh no.
Fixed. Okay, give it a go.
Air velocity when we're at the ground after crashing.
Find how much force he hit his neck with.
Oh, these are easy.
Good news, I don't have to solve that one. If you don't want to get through that's okay, but if you
Just cut them out individually.
Yeah, please, individually, yeah. And then separate the boys and the girls. Keep the boys and girls separated, but... What?
No. Yeah.
So follow your guidelines, folks. Identify the piece of information you're given. Is it R, is it the RDT? Is it A, is it the ADT? Is it C, is it the CDT? What are you given? Okay.
Oh, is it? Wait, the radius of the circle is 6 centimeters.
Yeah.
Okay, Ryan, let's go. Whoops. Yeah, you do.
What'd you get? What'd your answer get?
I got 8 pi and 4 pi.
Alright, perfect, so I got 24 and 12, so that means that. We got it right.
I used the wrong variable.
Hey, Ryan.
Yeah.
What?
You get some go.
What?
Take a field trip to Mars now.
I got the radius. It's 24 and 12. 24 pi.
Where are you going, Ryan?
Frederick High School.
So good shot.
Where are you guys going? Where are you going, Ryan?
Frederick High School.
Where that?
Frederick High School.
Let's go. That's in what?
Montgomery County.
That's Middletown, right?
It's in Baltimore County. We're actually going to the heart of PG County.
Ryan, are you online then?
Yeah. Okay.
Where are you going? Why?
Yeah, I'll get the text.
Why?
Why?
Hey, hook me up, fam.
Bring me Chipotle.
I'll text you,
I
Ryan.
have $20 on back.
Ryan, I'll text you.
Text me.
I'll text you.
Yeah, text me the picture of the money and with
You
your
can-
face.
you can have my debit card. Here, take my card.
And
My
your
card?
picture.
Here's this piece of plastic that you can't use.
They're going on a field trip to first school store. They want to get a school store here.
Stupid.
So you saw them like, oh, you can get a Frederick. And the only things they sell there are bullets and crack pipes. So. Woo! Never mind. I'm sorry, that was terrible. That was really bad. That was really bad. They sell pencil shit. God, I can't listen to it. You never would have heard that. Did you hear that? I'm very sorry. That was terrible. That was terrible.
The root of 2 pi. I win. I think I won. Oh, we didn't calculate. I think I actually did, but I think I won by. I think I figured them out. Yeah. I don't know.
Plus, the road's actually a lot worse than Frederick. In terms of like.
How do you know?
They both have gang presence.
Yeah.
TJ as well. So.
So does Walkersville.
So do we, but not to the same, not to the
Backwards
same
boys
extent.
represent.
They'll have like gang fights.
The Bill. The Bill gang.
We did the Bill.
The Bill gang. Oh, Bill gang.
The Backwood boys.
Hey, we don't talk about Phil games.
Bill gang. I think Stockton has the worst, not so much of a gang presence.
But there's what?
No, actually, the Catoctin has a big issue with like drugs,
Yeah.
meth and heroin. Yeah,
What does Walkersville have issues with?
who knows? I don't know.
I think it's with Almano.
But I think for the size of the school, for the neighborhood and stuff like that, there's a lot of like drug issues, like very serious drug issues. So very sad actually. People like overdose.
They call us Soror and heroin high.
That's what I call it, though.
So.
And then Mr. Way was like, prescription sales.
That's what it's more like, actually. I think.
Walkersville's like, chewing this, Bill.
It's like it's so addictive. You can get addicted the very first time you do it. Like.
Everybody's just so chill because everybody's on it. If they were doing it in the bathroom.
Yeah.
You would.
So.
I'm just here to focus on my
Very
math.
scary, right? So let's get to the math here real quick so we can get this over with. Maybe get you guys some time to start on your homework here. Okay. So let's go to someone we haven't heard from yet, Drew. Okay. So we want to find the rate of change of the area of the circle. So let's pull out some information we've got here first. What are some pieces of information we were given? Okay, the rate of change of the what? The radius. Very good. So we will say dr dt is 2. Okay, it's increasing at a rate of 2 centimeters per minute. So we'll put that as a positive 2. What else other piece of information are we given?
The radius is 6.
We want, at the radius, when the radius is 6, and we want to find what?
You want to find
dA dt for this first one, that's right. So dA dt equals what? That's what we're trying to find. Question mark. Okay? So what's the formula that we can use to relate these things here, Drew?
dA dt.
Well, let me start with A first, right? We start with
pi r squared.
A equals pi r squared, right? And then, sorry, go ahead. Now take the derivative, right?
dA dt
dA dt, 2 pi r dr dt, that's right. There you go. Welcome. Okay, and now we plug in, right? We're solving for dA dt, so we're going to leave this one where it is. It'll still be dA dt there, and that's going to equal, and then let's see, what goes in for r? 6. And what goes in for dr dt? 2. And so when we multiply that out, we get 24 pi. And again, our units here would be, we're trying to find, that's the rate of change of an area, so what would the units be here then, Drew? There you go, centimeters squared per minute, and that's it. Yep, very good. Questions on that one? We're all good with that? Thumbs up, rock and roll. All right, then, Jack. Rate of change of the circumference. Okay, we're going to use we're given the same information, so we don't have to do that part. What's the formula we're going to use here, though? C equals 2 pi r. Okay, and now what? Take the derivative. dc dt. dr dt. Okay. We're solving for dc dt, right? So we're going to leave that. That's right, so it's 2 pi times 2 pi times 2. So, thank you. And we get 4 pi. And what would the units be here, Jack? We're talking about a circumference. The rate of change of the circumference. Well, we know it's going to be per minute, right? That's hopefully clear. Okay. Well, then circumference. What kind of measure? It's just centimeters, right? Yeah, circumference is a linear measure. Even though it's like around the circle, it's still linear. It's only centimeters. Area is squared, and volume is cubed. Okay?
I don't know how people got
Plugged in the wrong number.
I was trying to do to say the answer, and he goes, yeah, you put 4 pi centimeters per second. He's like, no, it's not.
There it is. So you watch those units. Watch those units, right? Very important.
At least he tried. That's the worst.
Okay.
He's got roast. Tyler's got destroyed.